of the previously selected animation asset, the motion matching node will perform a blend into the newly selected animation asset, repeating these cycles every frame. With this understanding on how the matching is performed, let's introduce the database schema, the asset defining the matrix between poses, and specifying what we care to match. For example, the character feet positions and the future trajectory, and how much we care about those features via their weight. We define the schema as a collection of channels, simple building blocks, to match positions, velocities, headings, and phases, composable in more complex channels to match trajectories or entire poses. With the basics out of the way, let's continue our dive into the Fortnite motion matching recipe. Because of Fortnite's tight memory budget, we decided against dense cards. And instead, we started with well-crafted short animations with higher connectivities for those pose features we wanted to match, like character feet positions and velocities, to facilitate the motion graph's automated transitions. We also organize our animations in multiple databases driven by gameplay logic to discern pivots from start-stops, idles and run cycles, as well as being able to differentiate high-ends from low-end platform setups. But ultimately, we had little data that sometimes poorly matched our twitchy motion model. We knew we needed to construct motion matching queries that better reflects the manifold of our sample animation poses. So we started with manipulating the input trajectory generation by remapping motion model velocity and accelerations, as well as doctory rotation rates and filtering out spamming input behaviors. For moving platforms, Icy Feet, and Hot Pepper, we had to reconstruct historical trajectory and character pose informations to support moving reference systems and transition between them. The high frequency of animation shredding caused by motion matching in the context of a Twitch shooter put high stress on the inertial blend we initially adopted. Inertializing continuously between non-necessarily similar poses was causing visible extrapolation defects, like ripples in trajectories of fast-moving limbs. So we introduced a simple blend stack implementation. Blend stack is an anim node in charge of playing animation assets until their blend weight fades away, implementing a proper dynamic interpolating blend tree used by motion matching during asset reselection. We then use procedural behaviors to mitigate the discrepancies introduced by our doctoring between motion model and query, as well as the discrepancies between the query and the selected animation caused by the lack of animation coverage. A mix of stride warping and play rate scaling were used to compensate differences between the capsule and the selected animation speeds. Blend profiles with faster blend speeds on the character lower body were used to mitigate feet sliding during blends, and orientation warping helped bending the selected animation towards the requested input trajectory. And for better result, we leverage blend stack graph support to perform orientation warping on every animation in the blend stack prior blending them together, as you can see from the multiple green debug lines in the video. The final touches to the setup were made by tuning what we call continuing pose bias, a cost discount for poses playing as continuation of the current animation that allowed us to reduce animation shredding by sticking with the currently playing animation as much as possible. We also added block transition notify states to prevent jumping into sections of animations that don't play just right unless played from the start, like drastic turns or jumps, where you would never want to pick a pose after the character has left the ground. For specific assets like looping animation, we disable reselection of poses from the same asset, and we added a ring buffer, keeping track of previously selected poses to avoid repetition of past choices that would make it look less natural. And this is what we ended up with. And now I'll hand it off to Jose to talk about layering.
Sam gave us the recipe for high-quality motion matching. Now let's talk about layering and why it is a crucial part of developing a scalable pipeline in a live service game like Fortnite. We had to rework how all of our items were structured. This meant hundreds of weapons and consumables had to be rebuilt to use motion matching. For some context, before Chapter 5, Fortnite used per-item additive animations. There is one base animation set, and for each distinctive item, we manually author roughly 14 additive animations. Using motion matching, we can have hundreds of individual animations. So we ran into two challenges. One, we simply could not author hundreds of additive animations per item in the span of a season release. And two, even if we could, how do we fit this in memory? It became apparent very early on that to scale, we needed a runtime procedural solution. We used Fortnite as our R&D space. The first step was to reach our animator's quality bar. This graph is a simplified version of our prototype, but it shares the same core pieces from our approach. First, an unarmed animation selected by motion matching. Second, a frame of an unarmed idol to build a dynamic additive from. And finally, a static per-item pose to layer on top. We also had two custom nodes. First is Bone Mask, a dynamic layered blend per bone node that is data-driven. And second, Copy Motion, which extracts an additive transform of a specific bone and allows you to scale it and reorient it before applying it. This screenshot is from an earlier version of our approach, where we baked these curves offline. But we switched to our runtime approach, supported by motion matching's pose history, that let us dynamically delay the resulting curves in time. We could also tweak and edit the values on a per-item basis. Let's see how that looks. As you can see on the middle clip, the additive on its own was good enough for the body, but the arms looked very stiff. It was impossible to use the hand motions as is, because they're in the wrong direction. Using copy motion and pose history, we could reorient and delay the curves by just a few frames. This allows us to make heavy items feel weighty entirely at runtime. Finally, we apply this motion curve to our hand IK effectors and elbow controls. The next natural step was to apply procedural layering to a variety of motion match animations and see if the system holds up. These animations are from an early internal test, but the results were very promising, and it gave us confidence in the power of the layering approach. After this, we completed our setup, and we were entirely data-driven. We tied all procedural, all layering parameters, and even static poses to data assets. Animators could swap out and tweak values live using proxy tables and choosers. Shortly after, designers and animators were using these tools in ways that we didn't expect, by tying parameters to arbitrary gameplay behaviors. This culminated in the ballistic shield, where an animator was able to animate a complex item in only 1 hour, and with only a few poses. With this, our content pipeline felt solid, and we started production and conversion of all of our items. The next step was tackling the performance and memory challenges. Using choosers, we separated our motion matching databases into a dense and a sparse set. Our dense set had hundreds of animations, and our sparse set had less than 100. Thanks to improvements in the animation compression library, we saw savings of up to 16%, and we were able to fit the sparse set on the same budget as the previous system, including an additional slow walking set not present in previous seasons. As you can see, a dense set is much higher quality than a sparse set, but the sparse one still holds up pretty well, thanks to post-warping as well as time scaling. Unfortunately, last-gen platforms were still over budget, but we knew we wanted to bring the dense motion matching set to the widest possible audience that we could. And so, we began our optimization process. At this point, our new system was almost twice as slow than the previous season was. Our new nodes performed reasonably well. We could do better, but even untouched parts of the anim graph were slower than ever before. We recently introduced Fortnite to post warping, dead blend, choosers, and organized our setup into more subgraphs, among other things. This degraded performance and memory in unexpected ways, and we had a death by 1,000 cuts situation. There was no obvious single culprit to the performance problem. So we had to optimize everything. Our teams worked really hard in a variety of improvements to memory and runtime performance in various animation systems. These will be mostly available to you in 5.4. The animation attributes one was significant to us, so if you use them in your project or if you use post-warping nodes along with root motion, be sure to give this a try. And finally, after optimization, our performance numbers were similar to previous seasons, but with more post extractions, more animations, and with motion matching as the cherry on top. But last gen was still 15 megabytes over budget for the den set, and we were really, really close to reducing the number of animations in some of our most popular platforms. And then Jason Horner submitted this random change list that replaced a single line of code that costed us 17 megabytes. It's in the layer blend per bone node, so if you use them, this change is included in 5.4, and it will save you a lot of memory. And with this, we finally shipped. However, separately from the motion matching implementation, Chapter 5 shipped with additional movement model updates that were not well received by the community. Movement speed was slightly reduced, and the animations were already authored to match that. The Fortnite team reverted these movement changes, and we were impressed with how quickly motion matching let us adapt to it. We added 5-run loop and 5-run start animations to restore the style of previous season runs. We dropped them in our database, and it just worked. Then for all of the weapons of the chapter, we also tweaked all of our layering data assets to match the new run style. This would have been unthinkable in our old system. And with motion matching and layering, we did it in just under 2 weeks. That brings us to where we are today. We have higher quality animation. Thanks to motion matching, we have faster, more flexible layering workflows for item authoring. And using both, we have a future-proof system to power Fortnite in the years to come, or until something better comes along. That concludes the story of how we brought motion matching to Fortnite. I'll hand it back to Patty so that he can share how we're bringing motion matching to you.
Thanks, Jose. Now let's talk about motion matching for you, for your game. Motion matching will ship in Unreal 5.4 as production ready. And on top of this, shortly after 5.4, I'm talking a few months, we will also release a learning project that will have everything you need to get up and running with motion matching. Whether you're AAA or indie, we want motion matching to be accessible to you. That's why this project will not only be well-structured and easy to understand, it will also come with hundreds of animations available to you for free to kickstart your projects or pre-production. This is why it's going to take us a few extra months post 5.4. Please bear with us. I promise you it will be worth it. Here's another look at what was shown during the State of Unreal. This is the foundation for the sample project. Everything shown is full gameplay with no custom code. We also want this project to continue to evolve and expand over time, delivering more features, more animations, and quality for everyone. We will have more information on this very shortly. To us, this is just the beginning of motion matching in Unreal. We still have lots of features, workflow improvements, and ideas we want to try, to develop, and to deliver to everyone. Here's a quick look at some of the areas we've talked about expanding into. Root motion control and networked root motion solutions for teams to use. We'd like to use motion matching to generate content-driven blends. Multi-character motion matching, our plans for this focus around combat initially. Better tooling around generating and manipulating trajectories in the engine. More tools for artists to match their source data to the movement model. And of course, constant improvements to workflow and ease of use. Plus much, much more. And finally, a shameless plug for the team that put this all together. So go check out motion matching in 5.4. Thanks, everyone.
Welcome, everybody. My name is Jared Monson. I'm a technical animator, focused mostly on metahumans and character technology. Really excited to be here, and I'm waiting for my cues. There we go. Okay. Yeah, I'm a technical animator on the advanced character team, focused mainly on the metahumans and character technology. I'm very excited to be here together with my colleagues, Saga and Jacob, and also with Brian Klo with Klo Virtual Fashion. We'll be diving deeper into some of the main features of the Talisman project, seen in the State of Unreal video earlier today. We hope to pull back the curtains for you and give insights into the different techniques we use to achieve these custom visual styles in UEFN. We'll look at the metahumans, additional features added to UEFN, clothing updates, and then the environment that Talisman is set in. If you didn't get a chance to see the presentation earlier, here is a quick recap.
I'm glad you're here. The crew's been waiting for you, and we're ready to help you build what's next. Come on, let's go.
All right, if you didn't get a chance to see the full Talisman demo, I recommend you check it out on Epic's YouTube channel. Okay, let's further break down what we'll be going over today and how we'll get there. First, we'll go over a brief recap of what metahumans are, some basic knowledge to help you better understand the technical details we'll cover. And next, with metahumans, now in UEFN, we'll look at what we were able to achieve, the areas we had to consider, and then an overview of what we did to make this happen. After that, we'll look at the differences between an Unreal and UEFN metahuman, then get into the nitty-gritty details of what actually changed. Brian will join us to talk about Klo, their products, and their collaboration with the new USD clothing pipeline. And then we'll get to talk about some new clothing features, simulation tools that are now available in Unreal 5.4. From there, Saga and Jacob will take over and guide you through the Talisman ship and what it took to achieve this particular environment. We then should have some time for questions and answers at the end. So without further hesitation, let's get to it. Let's first start off with a brief recap of the metahuman ecosystem and the tools available for you to use on your projects. MetaHuman Creator is a cloud-based application that allows you to create high-fidelity digital humans. Through an easy-to-use interface, you can quickly and intuitively create photorealistic digital humans, fully rigged and ready to use. Through the power of MetaHuman Creator, you can make MetaHuman in minutes, starting from one of the preset characters or your own custom mesh to be used and customized in the Creator app. The MetaHuman plugin for Unreal includes Mesh to MetaHuman, which is an exciting feature that enables you to turn a custom mesh created by scanning, sculpting, or traditional modeling methods into a fully rigged MetaHuman. After converting your mesh, you can further refine your character in the MetaHuman Creator. Also available in the MetaHuman plugin is MetaHuman Animator. This feature set enables you to capture an actor's performance using an iPhone or stereo HMC, then translate that capture to a high-fidelity facial animation on metahuman characters. Every subtle expression, look, and emotion is accurately captured and replicated on your digital human. It's simple and straightforward and easy to achieve really incredible results, and pretty much anybody can do it. The animation produced is processed locally using GPU hardware, with the final animation available in minutes. MetaHuman DNA is an integral part of MetaHuman functionality. These files are created with MetaHuman Creator and downloaded with Quixel Bridge in UE5. DNA calibration is a set of libraries and tools used to inspect and modify MetaHuman DNA, bundled up into a single package. These tools are provided via GitHub repository for you to download and use to customize your own MetaHumans. MetaHumans are now available in UEFN, and this exciting news means that you can leverage all the tools available for the MetaHuman framework for your UEFN projects. Talisman was our internal project to test MetaHumans and push the boundaries of environments in UEFN, and we're really excited for you to use MetaHumans in your projects just like we did. All right, so you might already be aware that UEFN enforces certain restrictions for better user and player experience, and we were made no exception to this rule. There's currently a 2 GB total project upload size and a total download size of about 400 megs for a UEFN island. The average Unreal MetaHuman cook size comes in at about 800 megs. So that's 400 megs over the total allowed limit of one island. Basically, one Unreal MetaHuman is the equivalent of 2 full UEFN islands. Since we were going to be working within UEFN parameters, we knew we were going to have to get creative and come up with ways to pack in as much as we could, but only bring along what was absolutely necessary. We also knew we had to retain the high visual MetaHuman fidelity that we've come to expect. We ended up taking a hard look at every aspect of what made a MetaHuman and determine its impact on the overall outcome. Everything from textures, materials, grooms, animation performance, and meshes all had to be scrutinized. After a lot of hard work and effort, we're really excited to show you the results of what we were able to accomplish. Here is a one-to-one comparison of a UE and UEFN MetaHuman. The average Unreal MetaHuman cook size is about 800 megs, like I said before, while the average UEFN version is just 60 megs. That's basically a 93% reduction in overall size. You can see here that even with a significant size reduction, we were still able to maintain a high level of realism and fidelity. This achievement is what allows you to nearly have the same great visual quality in UEFN as you do in Unreal. As you really start to look at the picture closer, you might start to be able to pick out some of the differences, like the peach fuzz has been removed, some of the finer details like wrinkles and freckles aren't as sharp, and the overall features are a little softer, but even after pointing those out, the differences are pretty hard to tell. Here we can see a wider spectrum of characters with their upload size in blue and their cook size in purple for each of the 3 quality options that you can download. In the top right corner, we can see an average size of these characters. The average high-quality version for all of these characters is an upload size of 128 megs and a cook size of 55 megs. One of the biggest factors to the overall size of a MetaHuman simply comes down to the groom that you have chosen for your character. Despite whatever groom you choose, your actual cook size won't vary by much, thanks to optimizations done across all characters. This means you can choose virtually any MetaHuman and have similar performance and fidelity across the board. And the good news is that these great-looking MetaHumans aren't just reserved for high-end spec machines either. Here we can see the results of high-quality level UEFN MetaHumans. With your UEFN islands being able to be played on across all major consoles, we wanted to make sure every MetaHuman was looking their best, whatever console they were seen on. From high-end to handheld devices, you can expect good-looking results across the board. Going through this process of getting MetaHumans into UEFN led to many improvements and optimizations, and we're excited to share these lessons learned and insights gained. So let's dive in. while bringing metahumans into UEFN, we discovered functionalities missing for metahumans just to work properly. Adding these functionalities not only improve the quality of metahumans in UEFN, but also benefit all UEFN users. And here are some of the highlights. The metahuman component is a new UEFN-centric actor component that brings almost all the features that metahuman use from UE to UEFN. This is the central place for tuning the visual quality and performance of your character. If you want to create custom control rigs or physics assets for secondary animation, you can apply those through the metahuman component as well. Metahumans now work with the NPC device. We provide a basic set of NPC animations to get you started. The LOD sync component is available for you to use in your UEFN characters. We use it on the metahumans to ensure that the head and the body LODs match up. Groom assets are now also enabled and available for you to use. And we've added the ability to use recompute tangents at runtime for PC and higher-end platforms. And you can see here, this allows tangents to be updated on a deforming mesh, giving a much higher quality looking deformations. On the rigging side, we upped the per vertex weight influence from 8 bones to 12. The default bone influence is still set to 8, but if you require 12, you can enable 12. And panel-based clothing, which we'll expand on a little bit later, is also available for you to use. To help us get a better overall understanding of the differences between how a UEFN metahuman and Unreal metahuman are processed, let's take a look at what happens when you download your character. When you download a full metahuman from Metahuman Creator, you get the full unprocessed assets at their highest quality state. You then take that metahuman and do your own processing for whatever your scenario is, linear content to real-time applications. With an Unreal metahuman, you have the option to cook what and however you want, giving you complete control over the entire end-to-end process. For UEFN, we have chosen to pre-process assets and made decisions for you that make the most sense for working in UEFN. You have fewer decisions on how that character is processed, but the benefit is your asset is already in a great place for cooking into UEFN scenarios. The most important part that we want to iterate is that the underlying metahuman functionalities remain the same. In order to maintain compatibility with the metahuman ecosystem, we needed to make sure that what we reduce wouldn't affect your ability to use those great tools. With that in mind, we knew we wanted to use existing meshes without changing any geometry, as well as maintain the current rigs and skeletal hierarchy. These two areas we knew we couldn't or weren't going to change, as it would have an adverse effect on your ability to use those tools. This also meant we didn't need to create a new set of assets to maintain. The UEFN metahumans derive all of their assets from their Unreal counterparts, just tweaked to meet the needs of UEFN specs. In order to reach the performance benchmark that we needed for UEFN Islands, we determined 4 areas which we thought we could get the biggest impact and improve overall size and performance, while also maintaining fidelity. The 4 areas we felt we could improve on were reducing the overall amount of mesh LODs, general animation performance improvements, groom reductions, as well as textures and material optimizations. The area that we felt to start with was simply just to reduce the amount of the mesh LODs that we brought over to UEFN. When you download a metahuman, you have the option to select from 3 quality levels. High quality level is intended for metahumans that will be seen up close. It will take up more space in your project than a medium or low quality metahuman, but it should perform equally well when using LODs at a distance. Medium and low quality settings are simply stripped down assets of the high quality version and can be used when close-ups aren't needed or the need for greater performance is wanted. The mesh LODs that we chose to use are derived from the Unreal metahuman. Let's take a look at an image that might help you visualize this a little bit better. First, let's take a look how the UEFN metahuman level of details, or LODs, compared to the Unreal metahuman LODs. As mentioned before, UEFN LODs are derived from the original metahuman, but they're not a one-to-one mapping. Let's break that down a little bit more. We can see, based on the left-hand side, that a LOD 0 high-quality UEFN character is using LOD 1 of a UE metahuman face and LOD 0 of a UE metahuman body, and so on down the line. We chose these LODs because they have the highest performance and quality, with the lowest amount of footprint size. To maintain the fidelity of the neck seam, we chose the corresponding head and body LODs that assured those edges lined up and are properly synced through the LOD sync component. Now let's compare how the different levels within UEFN relate to each other. The high-quality UEFN character has a total of 4 LODs, while the medium has 3 LODs, and the low has 2 LODs. We can see in the graph that the medium and low-quality versions are simply just stripped-down versions of the high-quality levels. The next area of improvement we wanted to investigate was the animation performance side of things. We knew we didn't want to make any changes to the skeletons, but we felt it was worth looking into what we could optimize here anyway. By breaking down the animation compute distribution, we were able to get a better idea of what areas were taking up the most compute time and where we should start looking to improve. We noticed that the post-process NMBP was using a lot of compute time, and we realized we didn't have many options to tune that area. We then created tools that allowed you to take your metahuman from a fully enabled high-fidelity character down to only simply running just a skeletal mesh. Depending on your character, you can expect about a 20 times faster difference between a fully enabled and a fully optimized UEFN metahuman. We also made some generic improvements, like optimizing the anim graph and removing unnecessary functions. These improvements allow you to hit the quality and performance target you're aiming for. Maybe you have a few characters in your level and you want a high quality close-up, or maybe you have multiple characters and you're looking for a certain performance target. Now you have the ability to scale the post-process anim blueprint at certain LODs or switch it off entirely. These attributes are available and set on the metahuman component in your UEFN character blueprint. It's great that we have metahumans in UEFN, but you do need a way to animate them once they're in your project. In order to get your metahumans animating, there are essentially 3 ways we can achieve this. First, we can use a sequencer device. Using this device allows us to animate directly in engine using Control Rig. Control Rig is available in UEFN, and you can create your own rigs, just like you would in UE, and animate through sequencer. Second, you can play back an animation sequence directly onto the body skeletal mesh, just like you would in Unreal. And this can be any type of imported animation, such as mocap data or hand keyframe sequence. Last but not least is through the NPC spawner device. The NPC spawner device was released in Fortnite version 28.10, and we're happy to announce that metahumans are working with this device as well. The NPC spawner device gives you the ability to control the appearance, animation behavior, and modifiers of your NPC characters. After your NPC is spawned, you can further control their behavior through verse. When using the NPC spawner device, we provide a predetermined set of locomotion animations for your metahuman. This allows you to start immediately with an animating NPC, but the great thing is you still have the option to choose your own animations in place of the default ones. Now let's take a look at grooms. Grooms can be expensive, so we felt there could be a lot of potential savings found here. Our first challenge was just to get grooms into UEFN to begin with. Once grooms were enabled and working in-game, our challenge was then to make them optimal to hit the performance benchmark required by UEFN. Solving these challenges ended up working in our favor because we found benefits and improvements for both UE and UEFN. While this is not an extensive list, here are some of the groom improvements that have been made. Strand auto-lotting adapts the number of curves based on the screen coverage of a given groom. We can trim more of what gets simmed, interpolated, deformed, and actually rendered. This also allows for a smoother transition between LODs, which reduces the amount of popping between them. We've also optimized these curves for faster shadowing and ray tracing. Optimizations were done to textures that required the use of less textures, user-reduced texture resolution, and shrink the overall texture size. The new compact layout is packed into 2 textures for hair cards. The attribute map that contains coverage, seed, and depth in RGB is kept at a larger resolution for card opacity. It varies between 2K and 512, depending on the asset complexity. And the tangent map is packed together with strand view in the alpha channel. This map is between 512 and 256. In the Groom Asset window, improved debug tools are available for you to use, and further documentation about those tools is available on the UE website. Cook optimizations were also done, which reduced the cooked groom size by about 50%. One of the areas that we thought we could make some of the most improvements was on the material and texture side of things. Through baking textures, share-based material efficiencies, simplifying operations, and less instructions, we were able to reduce the material and texture size by quite a lot. Our look dev artists put a lot of time and effort into making sure the metahumans retain as much of the high visual fidelity that their Unreal counterparts have, but in a significantly smaller size. Now let's take a look at some of the details here. We knew we wanted to bake textures, combine maps, and simplify materials. When deciding how to bake the textures, we chose to use a combination of geometry scripts, Python, and blueprints, and Unreal rather than just C++. Working in blueprints allowed artists to iterate quickly without the need to change engine code each time we wanted to make an update. This also reduced the overall demand for time and support from engineers. Choosing what to bake essentially came down to choosing a balance between visual quality and memory footprint. Having look dev environments do A/B comparisons was critical to our artists in making the correct decisions, and you can see one of those A/B comparisons here. The high-quality MetaHuman has animated wrinkle map and face color maps. The medium version removes those animated maps, and the low has subsurface turned off with baked AO to bring back some fidelity. In the lower LODs, we also used baked grooms to save performance where it made sense, like eyebrows and some mustaches. For face materials, we ended up with 3 different material LOD versions. Each material has its own resolution setting, and is only used for the corresponding LOD level. The high LOD material has a max of 2K resolution, and this is the resolution cap for UEFN textures. The medium material has a max of 1K resolution, and the low material has a max of 512. We also decided to share one parent base material to be more performant, and allows all materials below it to inherit its parameters. For comparison, the original UE skin material was about 577 megs, and the new UEFN version is about 13 megs. All of the improvements that ended up being made, big or small, contributed to the success of metahumans in UEFN. The optimizations learned will also benefit the Unreal metahumans. You can expect some of these optimizations to be rolled into their Unreal counterparts. When all was said and done, and we look back at the overall impact on each area, here we see a rough relative scale of how much each area contributed to the overall reduction in size. Texture optimizations had the biggest impact, while grooms came in next. The one caveat to grooms is the complexity of your chosen groom has the biggest overall impact on the total size of your metahuman. Animation performance, by design, has the biggest range of optimizations, depending on how you choose to leverage those, and reducing the total amount of LODs was an easy win to start us off on the right foot. Up to this point, though, we had made educated decisions on what we thought would be the best areas to focus on, but we needed to really see these decisions in context. None of the final decisions were made until we could actually see the results in UEFN and evaluate visual quality and performance. And this came down to simply just looking at the assets in UEFN and doing tests. As mentioned in the slide before, having A/B comparisons and levels was really crucial to our success. Regardless of performance, we wanted to make sure we were maintaining the high level of fidelity we've come to expect. We did a lot of comparisons to determine what we could reduce and what we could not reduce in order to keep the visual fidelity high. We also realized that having an accurate representation of all the components that make up our metahuman was really important to assess the actual size and performance stats. To facilitate a testing ground, we created smaller individual projects and levels that maintain consistency with the main project to ensure accurate testing results. Creating these simple test levels in UEFN allowed for an easier and quicker way to evaluate those results and isolate problems without boggling down the main project. This is a quick video of some of our test levels. We set up different lighting scenarios, tested range of motion, facial animations, clothing simulations, crowd situations, size and performance scenarios, and really just about anything else that we felt we needed to test, as well as law stuff. With test levels set up, we couldn't make assumptions. We needed to see some real numbers. UEFN provides a tool called project size to help you see and evaluate those numbers. This tool gives you a breakdown of your project by asset type and the overall cook size that assets are taking up within your project. You can hammer down into each category and get more detailed information about each section. By reducing the overall cook size, you can fit more content into your project, and this tool helps you discover what assets are taking up the most space. We use this tool extensively, and it provided a tremendously helpful and valuable insight into not only MetaHumans, but the overall Talisman project. Now that we know all this information about MetaHuman, how can you get them into your UEFN projects? Well, the MetaHumans can be imported using the MetaHuman importer tool. It's very similar to what you're already used to doing in Unreal. You open the importer window, sign in with your UE account, and your MetaHumans will show up under the My MetaHuman section. From here, you can choose from the 3 quality levels available in UEFN, and this will download your chosen character straight into your project, and when that finishes, you're ready to go. All right, let's change gears a little now, and we can talk a little about some exciting updates to simulated clothing in 5.4. Clothing is an integral part of making characters believable and can be a visual expression of a character's personality. Creating clothing assets and getting them into your projects to use is not always an easy task. In order to make this whole process smoother and easier for you, we're very excited to now have a pipeline that allows users to integrate clothing assets from outside software packages such as Clo and Marvelous Designer. Clothing is important to MetaHumans, and having more clothing assets in MetaHuman Creator is one of our most requested features. We're also really excited to have partnered with the talented clothing experts at Clo in bringing this functionality not only to MetaHumans, but the Unreal Engine as well. We'll go into more of how we use Marvelous Designer and Talisman and show you details on how the Unreal to UEFN clothing pipeline works. But first, let's turn some time over to Brian to give us some more details about them, their Clo and Marvelous Designer software, and how their products now integrates into the Unreal Engine workflow. Please help me welcome Brian Kim to the stage.
Thank you, Jared. And hello, everyone. My name is Brian Kim. I'm a software product manager for Marvelous Designer at Clo Virtual Fashion, where our mission is to empower everything related to garments. For those of you in the gaming and VFX industries, which is most of this audience, our solutions primarily help designers with garments that your characters will wear. In addition to clothes, the software can also help with the development of anything that has cloth-like properties, including flags, sails, tents, as well as objects and creatures. Our technology, however, is not limited to the creation in the virtual world. We also serve brands and companies that are in the business of making real clothes, real garments, and objects that people wear in the physical world. Our solution covers everything from concept, design, manufacturing, marketing, fitting, and styling. If it's apparel related, our software can help. That's why our vision is to become everything, from the beginning to the end of every garment on Earth someday. So, cloth simulation used to be pretty niche, but the tech is so advanced now that many fashion brands are now using our solutions to make key product development decisions. Clo, our apparel design software, is trusted and used by many prominent fashion brands. By working with us, companies can accelerate their creation process and reduce costs while achieving higher quality and accuracy. Marvelous Designer is doing the same for the gaming, VFX, and filmmaking industries. Our software allows artists to achieve high levels of realism and quality with their garment simulations. And we were thrilled recently when the US Academy of Motion Pictures, which gives out the Oscars, gave the Marvelous Designer team a Scientific and Technical Achievement Award. It was an incredible honor that would not have been possible without feedback and input from the entire Marvelous Designer user community. So we would like to take this opportunity once again to thank everyone Thank you everyone for using our software. For us, it was a rewarding confirmation that Marvelous Designer is the filmmaking industry's tool of choice when it comes to cloud simulation. And with Epic Games, our motivation is to make 3D garment more accessible to our mutual user community through USD file format. Until now, Marvelous Designer users created artwork, including garments, creatures, and various assets based on our unique pattern-based workflow. However, bringing the artwork to another software has always been troublesome because of inherent limitations of using different file formats to suit user needs. Clothing-specific properties would be lost in traditional export and import process, and users would be left with a mesh that happens to look like clothes. We believe that USD is the key to an open and collaborative workflow for creating garments in Marvelous Designer and unlocking their true potential in Unreal Engine. Having an online vision with Epic Games has allowed us to identify what really needs to be done to realize a new workflow and openly work together to build cutting-edge technologies. Also, MetaHuman is something that our Clo and Marvelous Designer users have been asking for a long time. MetaHuman is crucial to us, as its technology will allow users to customize high-fidelity digital humans for more realistic and versatile digital fashion applications. With that being said, we want to ensure that MetaHuman technologies shine even brighter with realistic clothing created in Clo and Marvelous Designer. Unreal Engine users will be able to apply realistic clothing on their metahumans with ease to obtain stunning results shown in Talisman demo earlier today. Thank you for having me, and I'll hand it back to Jared.
All right, thank you, Brian. It really is awesome to be able to take clothing assets from high-end packages like clothing in Marvelous Designer, where clothing panels and parameters translate directly into the engine. With such an easy integrated workflow, it's clear to see it's a win-win for everybody here. This new process, which will be in beta in 5.4, allows you to easily see the real-time representation of your sim setup quickly. Once in the engine, you have the option to use those results in Unreal or send them on to be used in UEFN. At Epic, we used Marvelous Designer to create the costume for Rue, our captain on Talisman. Here we can see we use one of our stock MetaHuman bodies from MetaHuman Creator to construct the costume. You can begin your creation process by constructing your clothing in Marvelous Designer like we did. When working in Marvelous Designer, your fabric selections and simulation settings matter. If you choose to transfer those simulation properties during the USD process, we take into account those attributes and they will affect the simulation behavior in Unreal. Once you're finished in Marvelous Designer, the new USD export is an easy way to get your clothing assets out of Marvelous Designer and straight into the Unreal Engine. Once you've imported your clothing assets into Unreal, we can now start setting up the cloth panel graph. You can choose a workflow that ranges anywhere from fully automated to a completely hand-tweaked setup. This flexibility allows you to get something up simulating faster, as well as having the opportunity or the option to customize areas that you feel are necessary. At any point in time, the cloth asset can then be used in Unreal, or it can be migrated to be used in your UEFN project. In order to get your cloth onto your character, you simply add a chaos cloth component to your character's blueprint and choose the corresponding cloth asset you want to use. A new feature we've added is an auto-generated graph that's built when you first create a cloth asset node. This graph helps you get up going fast and saves you time getting started. This includes the USD import node, some core nodes for setting up the simulation, value transfers from Marvelous Designer if selected, a physics asset node, and parameters set to good initial values. The USD import brings in both simulation mesh and render mesh for you to immediately use. And just to be clear by what I mean by that, the simulation mesh or sim mesh is a lower resolution mesh that's actually simulated but not rendered. The render mesh is a high resolution mesh that you actually see. The render mesh is driven by the sim mesh and provides a higher detailed model without having to pay the computation price of a higher resolution sim mesh. We've also added some really great nodes for you to use in your graph, like auto skinning and auto lotting to speed up the creation process. And this feature streamlines the cloth setup, allowing you to arrive at a working simulation much faster and more easily. One of the best features of the clothing pipeline, though, is not only do we provide an automated path for many aspects of the pipe, but we also allow you to customize basically every part of that pipeline to suit your needs. For Talisman, we decided we wanted to have the best of both worlds. In this project, we felt there were assets that we wanted our artists to customize to fit our needs. For example, we created our own customized high-resolution render mesh for the captain's costume. The clothing graph allows us to swap out the render mesh for our own version in a really easy way. We also decided to use some of artist-tuned skin weighting for lot 0, and we used the remesh node to auto-generate lower resolution sim meshes for the lower LODs. In addition, we dialed in the simulation solver settings as well as other nodes to meet the needs of our project. But another customization we used is a really cool new feature which uses a kinematic collider. This is a deformable collider mesh that moves with the skinned asset. This allows for more accurate collisions at a relatively inexpensive price. The kinematic collider is really easy to set up in the graph and solves a lot of problems that come from just using capsules. The ability for us to customize the graph in areas that we wanted to, but also take advantage of the automated processes where we could, saved us time while also giving us creative freedom and control over the end results. With these features, you can decide what pipeline best works for your needs, anything from, again, the fully automated to totally customizable. Let's take a closer look at the clothing panel editor now. The clothing panel editor was released in 5.3 and introduced a new way of authoring cloth. The panel editor is where all your clothing graph work is done. There are 4 main sections to the editor. In the top left is the panel viewer, where you can see 2D and 3D representations of your asset, make selections, and paint weight maps. There have been a lot of tool improvements made here for easier painting and selection, and we'll continue to refine the tools and processes there. In the middle of the editor is the simulation viewer. Here you can view the actual simulation behavior, play animations, use different meshes to view your cloth on, and see the visual debug tools. On the far right is the panel for simulation details, preview scene settings, and the simulation visualization tools. The preview settings tab allows you to set skeletal meshes and animations to view your clothing with, and the details panel has all the usual settings that pertain to the clothing asset. The visualization panel has a lot of great features like seeing only the simulation mesh, displaying collisions, viewing weight maps, and simulation statistics, just to name a few. Last but not least is the data flow graph, and this is where you set up your graph and access the nodes to create different cloth features. It has a very familiar feel, similar to setting up and wiring nodes like blueprints. Once you're done setting up the graph in the panel editor, you're now ready to use your cloth asset in UE or export to UEFN. But before we do that, let's take a look at some nodes that might be of particular interest to you. The new transfer skin weights node is a new tool that we've added to the Unreal Toolbox for you to use. This node allows you to take an imported static mesh or asset come from the USD import and copy weights from a user-defined skeletal mesh to the chosen mesh. Since the cloth solver needs weights in order to work correctly, this is a great solution that skips the need for you to rig and weight your clothing mesh in an external DCC. In most cases, all you'll need is a rigged body, most likely your character or simplified version of it, and then your static mesh as inputs. The output of this node will give you a skin version of the static mesh, now ready to use for your clothing asset. It's worth noting that the algorithm we use in this node is different from what you might find in some DCC packages. The node provides an option for you to use a closest point on surface method if you wish, but the in-paint weight method is something that's quite different. This algorithm allows us to significantly better handle loose clothing as well as armpits and other tight areas on the mesh. And this method is a robust, non-data-driven mesh algorithm, which essentially means it'll work on any given mesh. You could also use the skin transfer even if you don't want to simulate your clothing. You can simply use this node into the graph without any simulation nodes, and the end result will be the rigged version moving with your character. And we use this technique for Lot 2 on our Talisman project. The remesh node allows for auto-generation of lower resolution meshes based on a target percentage. You can choose to remesh both the render mesh and simulation mesh, or just one or the other. For creating LODs and Talisman, we took a hybrid approach. We hand-created our render mesh LODs, but we used the remesh nodes to auto-reduce the simulation meshes. we decided to keep the same render mesh for both LOD 0 and LOD 1 as we felt the lower resolution wrapped better to the simulation mesh. And here you can see the numbers that we targeted for both the simulation and render mesh. Depending on your project needs and complexity, these numbers will be different for you. Now that you have the cloth asset all set up, getting your cloth asset into UEFN is really straightforward. At any point in time in your process, you can use the migrate tool to migrate your cloth into UEFN. When migrating your cloth, the only essential asset you need to migrate is the cloth asset itself and a physics asset if you've chosen to use one. Materials and textures are also available for you to migrate, but you may or may not need them depending on your project needs and if this is the first time you've migrated the asset into your project. The clothing asset bundles up almost everything you need into one asset, which makes the process really simple when exporting to UEFN. Rouge Jacket is 100% simulated using self-collision and a kinematic collider. Real-time simulation is not an easy task, and it's always a give-and-take relationship when it comes to performance and quality. Our goal is to make real-time simulation more widely usable and performance-friendly. You can expect a one-to-one performance and behavior between Unreal and UEFN, which is really cool. For Talisman, our goal was 30 frames a second on a high-end machine, going for high-end quality simulation in a close-up scenario. Our lower LOD simulation frame rates come in anywhere from about 50 to 60 frames a second after tuning the graph for those specific LODs. Total simulated vertices, self-collisions, and solver iterations being the biggest factors for performance. Our clothing tool gives you options as a developer. Whatever your budget is, real-time simulated clothing is a much more realistic option for you to use in your project. Our engineers and artists have been on the ground level using the system, and we're really excited to continue to push and develop it on all fronts. You now have the ability to import your clothing creations from high-end software packages like Clo and Marvelous Designer. The USD import process is what allows you to bring those clothing assets and to be translated into software packages into Unreal. You can utilize both automated and custom setups in your cloth asset graph. You can use a cloth asset in Unreal or easily migrate it into UEFN. And when this comes out in UEFN as early access, it will be released with documentation to help you get the best results from your assets in both Unreal and Marvelous Designer. The Clo and Marvelous Designer functionality will also be releasing at the same time 5.4 does. So at 5.4 launch, everything is unlocked and ready for you to use. We'd like to thank Clo for their work and their collaboration as we worked on implementing the USD format, and collaborating with the clothing and fashion industry leading company like Clo is really a wonderful opportunity. We're really excited to see what the community creates and leverages when making these and creating their own experiences. But even with the coolest looking characters, what's a character without an environment to live in? Talisman has a beautiful backdrop for our captain, and here to tell us more about the environment is Saga and Jacob. Please help me welcome them out now.
Thank you very much, Jared. Hello, everyone. Super cool to have you all here. My name is Jacob. I'm an environment artist here at Epic Games.
Hey, everyone. I'm Saga, a senior environment artist here at Epic. Seeing the amazing advancements on the metahuman side, we had our work cut out for us to achieve environments that match that quality bar. As an environment team, our goal for this demo was to build a huge, highly detailed spaceship to show what creators can achieve in UEFN when using their own custom content. Jared already touched on the project size constraints, and so just like the character team, we too had to seriously rethink our approach to content creation. While the 400 meg download size was often fine for most projects, keep in mind that ours needed to leave plenty of room in the budget for the metahuman character, custom audio, VFX, creative gameplay devices, among other things. With all these elements taken into account, we were left with just 200 megs to fit our entire environment into.
Now, in an attempt to provide additional context for how big of a difference this 200 megabyte target truly was for the entire team, I do want to draw a quick comparison to last year's Electric Dreams demo, for which we built an extremely detailed jungle environment. Really pushing the visuals and ensuring the highest degree of realism specifically for this demo, we created extremely high poly assets, which in turn took up a lot of memory. Even just a singular custom foliage asset variation shown in that demo clocked in at around 350 megabytes, almost twice exceeding our UEFN budget for the entire talisman. So essentially, we somehow had to attempt to squeeze an entire spaceship into the budget of half a firm. Now, with these constraints in mind, we knew that we couldn't just build the ship using traditional game mode workflows. We'd be over budget after essentially just building a single room. Then how do we work around that restriction? Let's dive into how exactly we approached building our environment specifically for UEFN.
Okay, so to do this, here are the main topics we're going to focus on. First, we'll discuss the typical challenges faced by creators when building their own custom environments. Next, we'll talk about the best practices we discovered to achieve a high level of detail in a tight budget. Following on from that, my friend Jacob here is going to do a deep dive into our fully procedural material framework, which was probably the biggest factor in how we managed to squeeze this massive ship into just 200 megs. Then we'll go into our Lumen lighting workflows and how we carefully balanced visual fidelity against performance to hit our target 60 FPS. Finally, we'll discuss memory management and the tools we use to get within the limits of the memory thermometer. Okay, so let's identify the primary challenges you might face. The first thing you usually need to consider is your project download size. Those 400 megs can start to fill up very quick when you're bringing in your own models and textures. You'll also need to think about how your project scales to each platform, from high-end PCs and previous gen consoles, potentially all the way even down to mobile. As well as visually scaling down, you need to worry about getting solid perf on each of these platforms as well. Finally, you need to keep your runtime memory limits in mind, as in order to publish your island, you've got to stay below the 100K threshold allowed by the thermometer. So with these challenges in mind, here are some of the fundamental best practices to follow when creating your own custom models. We found that the best approach for hard surface environments like ours were these mid-poly meshes with face-weighted normals. These allowed for nice mesh silhouettes and clean edge highlights without having to make normal maps from high to low poly models, which would be really expensive texture maps if we had unique textures for everything. Instead of trying to get all our details via normal maps or high poly meshes, we added them all via mesh decals, which is a topic we'll go into later in the talk. We also recommend working in a modular way, building versatile assets like these that can be creatively repurposed for a variety of uses. This kitchen area, for example, is fully built out of a small kit of repeating elements borrowed from other areas of the ship. We don't have any single-use, one-off models anywhere in the level, and instead built every room and prop out of this same kit of modular parts. So working this way massively reduced our project size footprint. For larger props that would be duplicated around the level, we just made blueprint actors. These props are all kit bashed from those same smaller pieces, and turning them into blueprints made managing asset updates and prop variations much more manageable than having hundreds of duplicate actors in your outliner.
So far we managed to keep our content cheap by either reusing most of it and also, well, reducing the complexity of our meshes. But we're still left with one massive issue, literally, in terms of memory budget. Texture maps add up quickly. Well, typically we expect textures to take up the largest amount of disk space, and we knew that if we relied on unique textures for our environment, we'd end up being over budget immediately. So we had to drastically rethink how we authored our materials for the talisman, stepping away from asset-specific textures completely to reduce their overall footprint in our project. So let's share some broad insight into how we approached a fully procedural, scalable material framework to solve our biggest size on disk concern. To start this breakdown, I want to briefly focus on what information we tend to use when texturing an asset. Artists usually rely heavily on baked ambient occlusion, curvature, and position maps as the foundation of creating high-fidelity texture sets. These baked textures give us and our tools context about the mesh we're working on that then allows us to modulate and mix different masks together. Now, reviewing the aforementioned base inputs for texture creation, we can start to look at how we might be able to ingest that data into our scene without relying on actual texture assets. For the talisman, the option that we landed on are vertex colors. To make this work, all our meshes were built specifically with clean vertex color data in mind. This means that we provide enough support loops to areas where we expect heavy interpolation, ensuring that we do have enough vertices to support smooth and artifact-free gradational values. Now, you already got a peek at our data packing in the previous slides, but we channel pack information in our vertex color channels just as one might do with regular textures. Broken down into their components, this ends up looking something like this. We're storing ambient occlusion in our red channel, curvature in the green channel that we can split into convexity and concavity just in our material, and then a mesh component-based ID map in our blue channel, which we can use to offset masks and tiling values. So just with that, we now store the basic building blocks for texture authoring directly in our meshes, at least in a rudimentary form, but at a fraction of the cost of storing them as unique texture files. Now, I do have to point out that dynamic and procedural materials are really nothing new. In most pipelines, you'll see combinations of techniques used to elevate the visual fidelity of an asset without having to force-feed the engine high-resolution texture maps. However, we'd still have to rely on unique per-asset texture data, such as specific layer masks, to make use of aforementioned features. And we simply did not have the space for them, so we kind of had to go fully dynamic. The basic principle here is pretty straightforward. We started by identifying what types of materials we actually need for the talisman in broad terms. That's metal, painted metal, plastics, rubbers, and some textiles. These main material types are defined by our parameterized base properties in our master material, heavily relying on well-aligned tiling textures, which we can reuse across the entirety of the ship. As we don't have the budget for unique mask textures to define which part of a mesh should be paint and which should be plastic, we separate out our material domains using the material slots of our meshes. From there, we further identified what additional layers will be required to tie these surfaces together and make them feel coherent. Primarily, this boiled down to general wear, scratches, scuffs, tarnish, grime, and dust. All these additional layers are equally driven just by a limited set of tiling textures and set up to make use of parameterized control wherever possible, all still in the same master material. By manipulating our vertex color data, we can now create a variety of dynamic masks, defining exposed surfaces and occluded areas, height gradients specific to either surface types or acids, as well as grime masks, hiding the lack of input data resolution by mixing in tiling variation masks and using additional world-derived data such as Z-vector-orientated faces. Those masks allow us to blend and modulate our detail layers to create believable accumulation of dirt and dust, and also wearing down exposed areas of our meshes. Tweaking our inputs carefully, we're able to convey logical and story-driven material definitions, such as dings, dents, and scratches, that are mostly focused around areas where the crew would bump into walls and corners. Now, we went to great lengths to sort of raise the ceiling on what can be done with such an approach, creating an incredibly powerful, robust, and most importantly, scalable material system, which was indeed kind of a bit of a huge challenge. But we really wanted to show what's possible and how far one can take the idea to inspire our users to experiment and create their own materials. While we don't have the time today to cover the materials in full depth, rest assured that you get to peek behind the curtain. All this content is going to be available very soon for you to dive into. That being said, we do want to share at least some specific insights and improvements that we brought into UEFN to help you in creating your own custom environments. First of all, to make it easier for our artists to switch between different surface textures for any given material type, the team added full support for texture arrays into UEFN. Because we needed ways of ensuring consistent texture tiling independent of mesh scale or orientation, we created a bespoke, optimized, dithered world-aligned projection approach that reduced the necessary texture samples all the way from the default 3 to just a singular 1. Our mesh-based ambient occlusion data is super important, but it really only considers the atomic acid, not the context in which the acid is used next to other objects in your scene. So to further enhance the feeling of cohesion of our heavily kit-bashed scene, we made sure to also ingest distance field-derived ambient occlusion. The incredible benefit of using DFAO is that it reacts to our set dressing. You can see here that grime and dirt accumulations update when our set dressing changes. Using it on top of our mesh-based data massively helped in really making everything in the level feel connected. To reduce the performance impact of our many material instances at the beginning of the project and their resulting draw calls, we ended up finding creative ways of storing material definitions for all of our different surfaces directly in our meshes. While this ensured seamless deployment to all supported platforms, this preset system also made it harder to modify the look of unique meshes in our scene. So this is where we're super happy to announce that custom primitive data is now fully supported in UEFN. Custom primitive data allows us to locally ingest data stored in the actor into our materials to override texture indices, change a vast amount of surface properties, and really minutely modify the amount of wear, grime, and tarnish without touching our materials or redefining our existing presets. Now, after all that work, we had created convincing, fully dynamic materials, adding high-fidelity visuals to the talisman without the need for any asset-specific textures. To level it up one last time and provide complex tertiary details like insets, screws, panel cuts, grates, and buttons, we made extensive use of mesh decals. Mesh decals are an incredibly versatile and equally resource-friendly approach to adding kit-bashable visual complexity to hard surface meshes. This really enabled the entire team to add visually consistent and convincing detail on the fly, either by creating mesh decal sets unique to specific assets or by adding them on the fly directly in the engine. All while actually only paying for a few base textures instead of really expensive meshes. To support this workflow properly, we added a custom bounded UV's parallax occlusion mapping function to UEFN that allows for artifact-free atlas projection. Excuse me, please. Delivering memory-friendly 4-3D details across the entire ship. That already, in its entirety, covers kind of the 60,000-foot view on how we approach the look of the talisman, at least from the material side of things. I'll let Saga take it from here to touch on lighting optimization, as well as our granular approach to memory management systems.
Thank you, Jacob. Okay, so next we'd like to touch on how we optimized our lumen lighting setup to carefully balance the trade-off between visuals and perf. This clip of the corridor lighting demonstrates many of the techniques we used on the rest of the ship. We're mostly using a combination of emissive planes in tandem with real lights. Most of our lights and static meshes are non-shadow casting, and you'll see why that is on the next slide. Now, I have to mention here that before we did these optimizations, the ship was running at it was struggling to run at perf, and so all of these techniques, I'm going to walk you through the way we managed to hit our target FPS. So you can see how these objects are not being hit by a direct light source. Lumen, thankfully, takes care of the occlusion and GI in these indirectly lit areas, even when the meshes have the cast shadows property disabled. So we found that disabling cast shadows on meshes not hit by direct light greatly reduced our shadow depth cost, improving perf without compromising the visuals in any way. Another really handy optimization we found was to fake the shadows of these overhead lights by adding a light function with a stripe texture into the spotlight. It's much cheaper than casting real shadows and gives us even greater control over the art direction of the ship. So improvements were made to the Lumen algorithm during the development of the project to reduce the amount of noise and flickering in Lumen. But while we were working on the project, we found that a great way to reduce the flickering even further was to dial the emissive intensity of our materials to really low values and to complement each of these planes with small radius non-shadow casting spotlights. So each emissive plane would have its own spotlight attached to it. We also encourage you to use the smallest possible max draw distance on your lights in order to cull them from view when you don't need to see them being rendered. Another handy technique is to press Alt-7 to visualize the light complexity in your scene. This is the technique that we use to minimize the amount of overlap between lights, and we went through the entire ship and tried to keep most of the level in the dark blue zone as much as possible. Finally, let's go into our approach for managing the memory thermometer in UEFN and look at the tools we had at our disposal before deciding on our final memory management technique. So with everything loaded and streaming disabled, the project was way over the memory limit, so we had a long way to go to get everything under 100K. We first enabled world partition streaming, but found that our unorthodox grid layout didn't work well with the square streaming grid. Our corridors were way too long in one axis, and you had to be able to see all the way to the end of the corridor without any actors visibly popping in. Adjusting the cell size and range to show the whole corridor meant we had way too much of the rest of the ship streamed in at any given time. Another problem with relying solely on world partition was that the ship had a lot of verticality. Our two biggest rooms, the common room and the cargo hold, sit right on top of each other in the z-axis, but world partition currently only works in X and Y, so when you were in either one of these two rooms, the other one was always fully loaded into memory. So the world partition team are working on implementing the system in 3 dimensions, but until then, we had to figure out another way to get this ship under memory. we decided that we'd need to manually load and unload areas of the ship depending on where the player was, and this is where data layers came into play. So to start with, we created a unique data layer for each room of the ship. The helm, the crew quarters, the corridors, the common room, each had its own layer with all the actors in each room placed in its corresponding layer. This includes all the geo, decals, lighting, post-processing, and effects for each room. Some of the rooms were really massive, and we didn't want to load them into memory all at once, as this was causing hitches. So we split up the larger rooms into sub-layers. The common room, for example, has 5 sub-layers split up by section of the room, such as the kitchen, the lounge, the hydroponic garden, etc. After creating all the layers, we dropped them into sequences and staggered the loading of each sub-layer in order to incrementally load them into memory. In these same sequences, we're also unloading other areas of the ship that we don't need in order to free up even more memory for ourselves. The following clip shows the general setup in action. We plug our data layer load sequences into these cinematic sequence devices and trigger them whenever the player crosses mutator zones around the level. We naturally try to place these trigger zones in places that completely hide the loading from the player, but here you're going to see what's actually happening under the hood when the player crosses one of these mutator zones. So this is what we didn't want you to see, but essentially each section of the ship is incrementally popping in as you're going through this common room area. Okay, so with all that being said, we hope you've enjoyed seeing behind the scenes on the creation of the Talisman project. Unfortunately, that's all we've got time for now, but please feel free to explore the project for yourself at the Epic Games booth. We have about 14 minutes left for Q&A, and this is where we'll be joined by some of our Epic Games colleagues to help us out as well. And if you have a question, please come up to the mic right there. I'd also like to welcome Jared and Brian back onto the stage for the Q&A as well. Thank you.
Hi there. I want to ask if, did you use HLODs or HLODs to prevent that popping and see if it fixes the issue with special loading, essentially?
Sorry, could you say it a bit louder?
HLODs, did you
right.
attempt to see how they work in?
Right.
Yeah.
We did think about using HLODs, but the way the level was built, it was kit-bashed out of thousands of tiny actors. And also, we were so tight in the memory budget that generating HLOD meshes would have probably taken us over the limit. So HLODs didn't really make sense for us to prevent actor popping. We also thought about disabling actors from being spatially loaded, but there would be way too many actors non-spatially loaded for it to make sense. So we just had to do the data layers approach.
That's good. Thank you.
Thank you.
Hi, my name is Chloe. I have 2 questions. Firstly, were any of your guys' models in this environment nanite-based?
Actually, yes, all of them are using nanite. I mean,
Okay.
nanite scales based on the platform. So for PC and the high-end platforms, nanite is enabled. And then as soon as we start trickling down to the lower-end platforms, we switch to regular static meshes.
Okay, sounds good. And then second of all, more for the environmental design, but did you guys use some sort of sociological aspects to creating your environment? So do you look at either real-world societies for your environments, or what aspects do you do to better create the digital society that this level plays into?
That's a really cool question, actually. I mean, when we start any of these projects, it's a big huddle with our guys and getting together and trying to understand what we actually want to build or need to build. And then it's a really creative process of just starting to essentially spitball and see what feels right. And then you go into the entire gray boxing stage and collecting reference images. And we didn't look out for anything specifically other than trying to fit into this sort of derelict-style spaceship. But there were certain things like the common room, for example, where it felt really interesting to have this weird kind of impersonal shared space with some areas that felt a bit more personable, but then giant robot arms and pipes just jetting in the middle of that room.
Thank you so much.
Thank you.
Thank you.
Any more questions?
We have lots of time, guys.
If not, that's fine too.
Yeah.
kind of off the cuff, but are there any like workflows that are traditional to Unreal Engine that you're finding that you really had to make a pivot to adopt UEFN? You know, like working well with UEFN with this level of visual fidelity?
Well, I would say if we're building environments in Unreal Engine 5, we're not worried about how much detail we're adding in there, nor are we worried about the number of triangles. Obviously, nanite means you can have almost infinite triangles in your Unreal Engine 5 scene, but the obstacle in UEFN is all of that becomes massive in your download size. So we've just had to rethink like how we got high fidelity visuals out of tiny assets.
Yeah, the entire base setup for how we approached this took, similarly to how you guys approached the metahumans, had us sitting at our computers kind of scratching our heads, thinking about, okay, how do we actually tackle that if we want to build a huge spaceship? Because we just came off from the Electric Dreams GDC demo that, as mentioned, single foliage variations clocked in at over 350 megabytes because we really wanted to push high fidelity. And so coming off from that and being like, oh no, we really need to think about how we author our content without just exploding the download size, that was kind of tricky. But yeah, that pivot happened pretty early on.
Yeah, same on the character side too. Like I said, we looked at our metahumans, like, holy crap, these are huge, and we have to get them into this. And so, yeah, it was a lot of head scratching. I mean, like, what do we start throwing out?
Yeah.
And so that's definitely a little different approach that we weren't used to.
Yeah, we also joked about like we could probably have kit bashed this thing out of individual triangles. Like that's how small it felt like the UEFN budget was. So it's
Hi again. So I want to ask, for example, in your example, you used data layers because it was a single player experience. So Fortnite usually has a multiplayer, asynchronous gameplay. So you cannot really use data layers because if a player is there, then another one is not, and you have to load everything essentially. Yeah. So how, are there any tips in terms of scaling this type of visual fidelity to have multiple levels? Because also in UEFN you cannot have more than one level, so you cannot just reset memory essentially.
Yeah.
So are there any tips in how we can scale this to say one extra spaces outside the spaceship, say planet?
Yeah, that's a really great question. I never even thought about it until you brought it up, but I would say think creatively about what your gameplay is in those scenarios. Like maybe your multiplayer arenas are confined so players can only be in one arena at a time potentially. I think it just involves like out-of-the-box thinking in terms of what you can do with your gameplay, because it is a real limit that obviously asynchronously you can't have players going through different mutators on gates and loading in different sections independently. Yeah, that's a huge challenge.
All right, thank you.
That's a great question.
Yeah, that's a really good question.
Hello.
Hi.
So consumer devices are getting more and more capable, larger color volumes, brighter displays. What techniques can a developer use to go ahead and take advantage of some of those brighter displays without messing up SDR or vice versa?
You guys know?
That's a great question. I personally don't know. Let's see if any of their colleagues, anybody have any ideas on that one? You have a great question that stumped us all, but there is somebody at the booth, I'm sure, that can help you. So please bring your question over to the booth, and that might be able to help you.
Thank you.
But thank you.
It's a Rod Stewart question.
I know.
Really good question.
Yeah, it's a question for Rod.
Yeah.
Got someone coming down.
Yeah.
Hello. I wanted to ask how you broke down the huge procedural challenge that you had between your team, breaking it down into so many assets. How did you manage that within your team?
Well, so the good thing is, kind of cool question again, our team is relatively small to begin with, so we don't have to manage 120 people and figure out, okay, who's working on what. And especially at the beginning, this was a bit akin to shotgun development approach, or throwing stuff at the wall and seeing what sticks, in the sense that we started with just the corridor and trying to figure out, okay, what do we want this corridor to look like, and how can we split out certain parts to reuse them? And then this corridor became our visual or artistic touching stone to understand, okay, this is the style we're going for, and from here we can just expand to the to other parts of the ship.
Yeah.
And during that entire process of expanding into other areas of the ship, we just found more and more use cases for the assets we already had. And if we found areas where we didn't have any assets to use for, then we actually started in creating new assets. So I think pretty much for 3/4 of the entire project development, we were still adding assets to the roster while also deleting old stuff that we noticed we don't actually need and we can replace with other content.
Yeah.
So there was no grand master plan going into this. It was literally just, okay, let's try to figure out how we can make this work.
Yeah, like we were totally winging it. We didn't do it the right way to start with, and we pivoted dozens of times. But at the beginning, we were just modeling, like normally, like as you would normally design and model a part of a ship, and figuring out what were the common geometry elements that we needed in different areas of the ship, and then starting to reduce the amount of assets we had just by stripping down, like that section of the door can probably do with having that section of the hallway, and just like creatively repurposing assets where we thought they made sense, and using that to get rid of additional meshes that were extraneous to the project. So it was trial and error and just like figuring out what we could cut. Yeah, it was a long process.
Like figuring out how we built something like this, something so complex for UEFN. We had no prior experience in that in our team, so we had to make some well-informed decisions at the beginning, sort of like the MetaHuman team is seeing like, okay, what are our easy wins? And then going from there and trying to be more informed based on what happened during the project. I hope that answers the question.
Yes, thank you. And since I don't see anyone else, I'll ask another question. So is most of the lighting baked lighting?
No,
No?
it's all just lumen. It's all fully dynamic lighting. There's no baked lighting in UEFN, period. That was one of the biggest challenges, is there's no sun hitting any of this stuff, so it's all like really soft indirect lighting, which without baked lighting is in games a huge challenge. And when we first threw our initial pass at lighting in there, there was a ton of flickering, and we had to go through all of these like sort of trial and error phases that I showed in the lighting section to reduce the amount of flickering to the point where it's barely perceptible. But yeah, that was a big challenge.
Awesome. So are they, did you have to touch the light maps very much?
There's no light maps whatsoever. You can't have light maps in UEFN.
Okay.
Yeah.
Thank you.
Thank you.
No worries.
Hello, I had a quick question with environment art. I've tried baking my weighted normals before, but they don't work if the mesh is open. Do you guys, is all your meshes closed, or do you guys have a different method of baking your weighted normals?
We do have some open meshes. We approach, because some of us were using one DCC, and then another of our environment guys would be using another DCC to author their meshes. But we used weighted normal modifiers on a lot of them, so it wasn't a full baking pipeline that we went through. And that actually worked surprisingly well on open meshes too. With weighted normals, you have to be, well, a bit cautious, and it can be finicky sometimes, because you expect a certain result, and then the software just throws you a different one that you didn't quite expect. And then massaging the polys in a way that they give you what you need visually.
Yeah.
Okay.
But there was no magic sauce on that.
Yeah, no, the meshes aren't perfect. Like, we tried to get rid of shading artifacts by manually adjusting normals as much as we could, but it was a lot of like manual work as well.
Okay, cool, thank you.
No worries, thank you.
Hi.
Hello.
They keep coming. I was wondering, for the kit passing, say the robot arm, for example, was it better to design or place the modular elements in the scene, or make a blueprint prop and do it in the blueprint prop editor?
That's a good question. We initially had, well, we had two versions. One was a blueprint version, but that was very unwieldy to animate in sequencer. So we have a non-blueprint version, which is just arranged in the outliner in a highly organized folder, and that's all like keyed in sequencer. So we have two versions.
Okay, and which one would you recommend as a designer?
I would recommend as much as possible using blueprints. Go
Yeah,
ahead.
any actor container part, so any prefab system in that regard is way better when you use to set dresses.
Yeah.
Because we were using meshes in a very unorthodox way in creating these different modules out of pieces that were never intended for it. And then wanted to animate it because it looked kind of cool.
Yeah.
We did have to go through and break it out of the blueprint so we can organize it directly in the outliner, so we can then use parent assets that we can animate in sequencer, and the rest of the arm kind of follows along.
Yeah.
So for these very complex, non-rigged, kit-bashed mechanical pieces, having them in the outline and organized there is probably one of the only ways to do it nicely.
Yeah.
For any other just static prop, always, especially when it's kit-bashed, always use an asset container like blueprint assets.
Yeah.
But ideally for this, if you plan for it properly and have many, many uses for it that you know of, I trade a rigged mesh, like a unique rigged mesh, and then you can create animation sequences or rig it up directly in engine and animate it in engine, which is much more of a nicer workflow and kind of more streamlined.
There's been a bunch of talks happening around scene graph. We didn't have access to scene graph when we built this project, but going forward, instead of blueprints, I would say scene graph would be the way to generate these hierarchical components.
Sounds good. Thank you.
Thank you.
Hello.
I think that's.
We'll get one more.
We'll get one more.
We'll get one more.
Last one.
So in regards to the plants, with people being pretty good at spotting patterns and things, and they're very organic, and you didn't have a lot of space for multiple different versions of plants.
Yeah.
How did you go about maintaining the organic and not patterned feel of them?
I mean, if you play the demo, you'll see there is a lot of repetition. We tried to minimize it as much as possible. I think there's 3 plant variations in there, but it's really not a lot. We wish we had the budget for more, but yeah, it's just non-uniform scaling stuff, like arranging them in creative ways. But yeah, you'll notice repetition for sure.
Okay.
And it comes down to sort of high quality asset selection too.
Yeah.
So there are assets that if you duplicate them next to each other a few times and rotate them around, you can scale them however you want. They will look like they repeat. And others hide that stuff really well. So we went through multiple cycles in the project of identifying, okay, these assets we can repeat 100 times and you won't really notice. And so we focused on staying with these assets specifically. And so the plans are kind of a testament to that.
Okay. Thank you.
Thank you very much.
Thank you, everybody.
Thank you, everyone.